Welcome to this video on regression analysis. Now, in this video, we'll cover some of the most popular regression algorithms that are used in data science and show you how to use them in R with the wine dataset. Now, regression analysis is a very important statistical tool used to analyze and model relationship between the dependent variable, sometimes called target or outcome, and one or more independent variables, also called input variables, or predictor variables. Now, this allows us to make predictions and estimate the impact of different factors on these independent variables on the target variable. Also, we'll explore the following algorithms: linear regression, ridge, support vector machine, k-nearest neighbor, decision trees, random forest, and neural network. Okay, we'll go through each of these algorithms step by step and show you how to evaluate their performance using some of the common metrics such as RMSE, mean absolute error, and R-squared. So let's dive in and get started with regression analysis in R. So a little bit about the data set. So this is just a wine data set, consists of 13 features. And this includes all this with a brief explanation. So the target variable here, what we want to predict, is called quality of the wine, which is rated on a scale of 0 to 10. And this data set contains the following observations: 6,497 observation or training examples, with 1,599 observations for red wine and 4,898 observations for white wine. Okay. So the goal here is to predict the quality of the wine based on this, what we call physiochemical attributes. Okay, this will involve building different regression models that will try to predict the quality of the score of a given wine based on the chemical properties such as acidity, pH, alcohol content, and so on and so forth. Okay. So the first thing we want to do here is to load the required packages. We've already seen this from the previous video on Titanic dataset on classification. So, so we're going to load all these different packages. If not, you can always uncomment that and just plug in all these packages that you want to install. And then once you're done, you can comment that back. So tidyverse for data wrangling, caret for model creation and evaluation, and sometimes also comes with KNN for k-nearest neighbor, rpart for decision trees, random forest metrics. This allows us to access the evaluation metrics for binary and multi-class classification if you're using confusion metrics for a classification problem, right? Also, it contains evaluation metrics for regression such as RMSE, R-squared, and so on and so forth, and also for clustering problems. The E1071 package, we can access the SVM support vector machine, naive base here for k-nearest neighbor, neural net, and NNNet for neural network. Then here, just a faster way to reference our data or our file in our current project. So I already loaded this. So this is how to load it. I'm gonna just use read.csv. Once you load it, the next thing you want to do is do some data pre-processing. Okay, this is very important. So the first thing you want to check and see, do you have any missing data, right? So we run that. So fortunately, we don't have. This is a good example here. So suppose we had some, missing values. You could actually create different objects here, so we can use another package that just tries to impute the missing data using the median, or you can impute that using mean, and so on and so forth. But since we don't have, so we'll just continue. So the next thing is to split the data into training and test data. So let's go through each of this code. So the set seed here, this line of code just sets the random seed to 123. We can change it to any number, right? This ensures that any random processes that we use later, especially splitting the data into training and test set, will be deterministic. In other words, we're saying that the meaning, the same random process will be repeated each time the code is run. This just allows us to maintain reproducibility of the results. Okay, the next here line of code is a create data partition. Again, this is just a function from the caret package, this package over here. Again, this just allows us to split the data into training and testing set. And then this P parameter here tells R that we want to split, specify that 70% of the data should be used for training. And the rest of the 30% will be used for test. Okay. And then list equals to false here. Just says we want to return a vector of indices rather than a list of data frames. And then the train data here object, okay, this line of code here, essentially what that means is that we want to use the vector of indices that we just created previously here. Okay, so with that, again, we just want to return, 70% of the rows, right? Remember the 0.77% of the rows here will be regarded as the training data. Okay. Again, so we assign this to this object, train data. Similarly here, again, we are just saying we want to return the 30% of the rows from the wine data set as the testing set and assign it to this object, test data. Okay, so we run that. We've already created that. The next thing is to now go to modeling, right? And our first algorithm is linear regression. Okay, so let's quickly go individually through this. So again here, if you're going to be using cross-validation, let me just remove that. So this line of code, what that means, so first of all, this train control function, okay, it's just from the caret package. And you can see from the tooltip, you can use the different parameters. Here, the method here, we just say, we want to use cross-validation. That's what the method CV just specify that we want to evaluate the performance of the model, right, using cross-validation. And then the number here could be 5, 10, or whatever number. You just specify the number of folds, okay, to be used for cross-validation. In this case, this is just we want to split the data into 7 equal size folds. Okay, basically just sampling method. So I'm just comment that back. Again, so that's with cross-validation. Again, so without cross-validation here, this is what we have. So we just use the linear model, right? So this function just comes with R, right? So essentially, it's used to create a linear regression model. So let's look at what this means, right? So again here, the quality here, so the quality tilde dot notation here essentially means that this is just a formula that specifies the model, where the quality here is the target or the response variable, right? And then this dot here just means that we want to use all the other variables in the dataset as predictors, right? So this tilde just separates the dependent variable on the left-hand side and the independent variables on the right-hand side. Data here means we want to get our data from the trained data. Okay. Okay. Again, here, if we're going to be using the cross-validation, train function here, again, just comes from the caret package. We've already explained that. And then the data just come from a trained data. And then we specify the method. Again, the method here will be linear regression. And then here we just want to say we want to use this CV, which just comes with the cross-validation. So CV here will correspond to this. Okay. But since we just want to build a linear regression model without cross-validation, we're just going to use that. Okay. So next, we're going to be using the predict once we create our model, right? So we store it in this object. And then we use the predict function here. So this predict function is just a function in R used for making prediction using a trained model. Okay. So here our linear, we're going to pass our linear model that we previously created in the previous step. And then we also want to, compare that, right? So this is our predicted values, right? And we want to compare that with our new data, our test data. This test data is the 30% that was previously unseen. Okay. And this is just a data frame containing the test data. So once we do that, we store it in this object lmpred, And then now we start evaluating using RMSE, right? So RMSE here essentially is just a function from the metrics package. So metrics package, remember we loaded this metrics package over here. So RMSE here, we're just gonna, in fact, RMSE, if you recall, just calculates the root mean squared error, right? Between the predicted, so the predicted values, which is just LM-pred. So LM-pred is contained here. And then we wanna compare with this specific, this is actually our actual data, the test data, right? So this test data $ quality, right, is the vector of the actual values for the response variable in the test data, okay? So we're gonna be doing this for both the mean absolute error and R-squared, right? So again, we can see here R-squared is just a function from the metrics package that calculates the coefficient of determination, right? This R-squared is also known as the coefficient of determination, okay? Between the predicted values and the actual values. Similarly here for mean absolute error, we just want to get the mean absolute error and compare that between the predicted values and the the actual values. So once we have that, you can run that, you can see successfully there are no errors. Then we move on to ridge regression. Now, ridge regression here is a type of linear regression that includes regularization, right? This regularization term in the cost function is used to prevent the overfitting of the model, right? So how does it implement this? So in this example here, we can see that we use method equals to GLM net. Okay, so this GLM net contains the following: L1 and L2 regularization. Okay, this is what allows us to penalize our model to prevent overfitting. Okay, so, and again, the good thing about ridge regression, it can handle both continuous and categorical predictor variables, right? So with cross-validation, again, this comes from the carrot package. We've already looked at that. So we want to regress our target variable across all the independent variables, or predictor variables, and we want to get the data from the trained data. Method here is GLM net. Okay, ridge regression just contains just a variation or linear regression that has a regularization term in the cost function, which is good to kind of mitigate overfitting. And then here, this is our cross validation that we already initialized previously. Okay, so again, without cross validation, essentially we just take this away. We take this away and then just maintain that. Okay, the same also remains the same. We just repeat the same procedure here. So we click on run, and that successfully computes or is executed. Similarly here, this is straightforward SVM again here, without cross validation. So again here, we just want to fit an SVM model over here. Okay, so this function SVM uses a radial basis kernel, right? So it uses a radial basis kernel, okay, by default to fit an SVM model. Okay, however, we can also use other functions. So with cross validation, we use train here, and it allows us more parameters. So as you can see here, we have SVM radial. In fact, you can use the help function here to just look through the different parameters. So you can see here some of the available methods include, so if I go over here, you can see, let's see here, you can see a different kernel, right? Other kernel, we can use linear, polynomial, radial basis, and sigmoid. Okay, each of them have their different strengths. Okay, the tune length here equals to 10. Essentially, what that means is that we want to specify the number of values to be tried for the tuning parameters of the SVM model. So in this case, the 10 here just means that we want to try 10 values. Okay, that tunes this radial kernel parameter. Okay. So since we don't want to use cross-validation right now, just comment that. So we're just going to use the basic here. The same, so again, we predict and then we evaluate using RMSE, mean absolute error, and R-squared. Once we have that, we execute that. Okay. Then K nearest neighbor also is another type of algorithm that we can use. So there are different packages we can use here. So we can use the one from Caret package, especially when we want to use with cross-validation. Train just comes from the Caret package. The only thing here that changes is that we specify we want to use the KNN. Everything remains the same. The number 10 here is, essentially I could replace the entire thing here with CV. Okay, CV here, the one that we already initialized over here in linear regression. Remember this? So CV here just says that we want to use 7 folds, right? But again, what I have done here is to show you that you can also do this inside, you can actually specify this explicitly, inside the equal sign. So regardless of what you prefer, either of them is, each one of them should be fine. Okay. So I'm just going to do that. And then also without CV, again, the only thing we've removed is this part here. Okay. So everything remains the same. Okay. Should you decide to use the KNN, double KNN, so remember this also package that also supports K nearest neighbor. So the difference here is that, unlike using the KNN from the Caret package, this double KNN additionally includes kernel weighting or local scaling. Okay. This can be very useful, especially, when you have some nonlinear functions, right? Your data also requires you to use some nonlinear functions. Okay. So with that, let's go back here. You can also implement this code over here. Okay. Where everything remains the same, especially except here K equals to 5 just specifies the number of K nearest neighbor to be used in your model. You can change it to 3, 5, 1, and so on and so forth. The kernel here, triangular, essentially what this means is that the triangular kernel means that you want to give more weights. Think of it as a triangle. You want to give more weights to points that are closer to the target point and less weight to the points that are farther away. So this is what it means. And then scale equals to true, specifies whether or not we want to scale the predictor variable. Remember, a predictor variable, the independent variables, we want to scale the predictor variable in the model, right? In this case, true what just means that all the variables are scaled to between 0 and 1, meaning that it has a mean of 0 and a variance of 1. Okay, so this is really cool, especially if you're using this kind of algorithm package. Okay, so I'm just commenting that out. We're just going to use the basic here. So again, after that, once we create our model, we kind of predict, compare the the predicted values with the true values, evaluate that using RMSE, mean absolute error, R-squared. Okay, we run that again. And then decision tree, again, it's the same thing. If you're going to be using cross-validation, we're going to use the train package, or rather train function from the Caret package. The only thing here we're going to specify again here is that we're going to specify we want to use the R part, which tells R we want to use the decision tree. Okay. So on the other hand here, if we just want to directly use that, then we're going to say R part, this is from the R part package, decision tree. Again, this is our target variable. The tilde here just separates the target variable with the independent. The dot here just means we want to use all the independent variables from this trained data. Okay, and then the method ANOVA here is the default, especially if we're going to use decision tree. Again, ANOVA here just means the analysis of variance. Here we just specify that we want to use this as the splitting criteria in our model, right? Remember, we also have other criterion like Gini, entropy, class, and so on and so forth. Okay, so all these are just different criterions that we can use to split the variance of the response variable. Okay. All right. So this just helps us to find an optimal split. Okay. So again, Gini here is just another very popular method. Just determines the impurity index, the measure of quality of a split, mostly used for classification problem. Then entropy here, I believe also, it just uses, it uses information gain based on the entropy. Okay. And it just measures the quality of a split. Okay. This is also very common with classification problem. Okay. All right. And I think others include also exponential and so on and so forth. Okay. And how to use that. So if you're interested to using that, you just you're gonna just pass this part here. Okay. So you just paste that over here. This is the parameter that you're gonna be using. Since we don't need that now, we're gonna be using analysis of variance. Okay, in our case here. All right. So once we have that, again, we repeat the same procedure and we, give appropriate names to our tree so that we can call them and summarize later in the bottom of the code, the project. All right, and then random forest here is the next. So the only thing that changes here, so if we're gonna just use without cross validation here, n tree, essentially what this means, this parameter just sets the number of trees in the random forest. Okay. To 2000. We can change this number to 500 if you want. Okay. And then the importance here equals to true. This parameter just specifies that the importance of each variable in the model should be calculated and reported. So we want to see this. This is what we are more concerned with. Okay. And again, here the importance of this variable is just a measure, right? It's just a measure of how much those variables contribute to the accuracy of the model and can be used to identify some of the other important features in the data set. We'll see another function that we can use to just kind of summarize that for us. Okay. So once we have that, again, with the cross validation, the only thing we change here or include is just this part here. So just keep that in mind. All right. So that might take a little while because we are trying to, use 2000 trees. So remember, this is just the decision tree, one tree. It kind of just use the idea of wisdom of trees, right? And then I'm just going to quickly explain this. This might take a while, so I'll skip this. I've already run it. So neural network here just implements, if you recall, what you call a feed forward network. So what that means is that, this type of network is a type of artificial neural network, right? Where the information flows from the input all the way, it flows in one direction, all the way to the output layer, okay? So in between here, we have something called, so let's say we have that there. So in between here, we have something called hidden layer, okay? So we have hidden layer. So now let's look at this. So from this package called neural net, again, so this is our formula. We just want to get the relationship between our target variable and all the independent variables, out of this training data. Then we want to specify that our hidden layer, we only have one hidden layer. Okay, so think of this of one hidden layer that has 5 neurons. What if you want to include more hidden layers? So just use the C concatenate. You can say we want to include 3, 2, right? So what that means is that we have 2 hidden layers, and the first layer, hidden layer, has 3 neurons or nodes, and then the second hidden layer has 2 neurons. Okay. Step max here, essentially, this parameter just means that we want to specify the number of iterations or steps to be performed during the training process. Remember, this uses propagation. So one epoch is just one forward pass and one backward pass. We call that an epoch of the entire training data. So essentially, you can imagine, this parameter is used to just prevent the algorithm from running indefinitely, right? So this is almost like 10 million times, right? Okay, so 10 power 7. Then linear.output equals to true. This is another parameter, specifies whether the output for this neural network, okay, should it be linear or non-linear, right? In our case here, we want to set it to linear, right? Non-linear can be very useful, especially you want to model relationship, between response variable and predictor variable, right? And because here we are dealing with numerical target variable, then we can just put it as true. Okay. So overall here, our network here is a popular choice for training neural network models. But one thing you need to keep in mind that, this neural network is a very complex model and works very well if you have very large data set. If you have small data set, then, clearly you'll see some overfitting or it will just perform very bad. Okay. Again, what makes this very popular is just allows flexibility, right, for specification of the network architecture. Okay, meaning that you have so many parameters that you can fine tune to improve the performance. So here I just quickly included learning rate. That's another hyperparameter we can fine tune. We have momentum and so on and so forth. It's just beyond the scope of this video. Okay, again, we repeat the same procedure. So I'm not going to run this. It might take a while. So already run that. Again, this is another code. If you're going to be using NNet, this is another package. So this is how to do it. So here I just implemented the train package from, from Carrot. So I'm just going to quickly go over this. So here, as we just specify the algorithm we're going to be using is called the backprop. Okay, backprop means backprop propagation. It's the most common use to train neural network. Line out is true, meaning we just want to indicate that the output of the neural network should be linear. Since the target variable in our quality is numeric, then we believe this is just the most appropriate for regression model. Okay, trace equals to false here simply just means we want to prevent the function from printing the progress update during training. We don't want to see that. Max here just sets the maximum number of weights to 5,000. And max it, we just want to say that maximum number of the iteration for the optimization algorithm should be 1,000. Okay, so once we create our model, including cross-validation here, using this package over here, or this function here, the same just remains. We predict and we evaluate using RMSE, mean absolute error, and R-squared. Okay. So again, these are the results. So here, this output here, essentially just, this is just a table. Okay, so we summarize using this table. So essentially here, we just create a text of all the different models we want to see, and then we concatenate all the RMSE, put it as RMSE here, concatenate all the, mean absolute error, and we combine all that in a data frame. So we print that one out, and we can already see this is what we have. Okay, and lastly, let me just quickly talk about this variable importance, or maybe let me just talk about this here. So we have RMSE here, and we know that RMSE here ranges from 0 to 1. The lesser, the better, right? Then R-squared here, very important parameter as well. Again, the higher, the better, right? That means that if it's 100%, that means the independent, the model is explained by the, the target variables, variance is explained by the, independent variables, right? So in other words, the R-squared is just a statistical measure that represents the proportion of the variance in the dependent variable, right? In our case, quality, that is explained by the independent variables, right? All those the chemical properties of variables, right? In our models, in all these different models. Remember, R-squared is also known as the coefficient of determination. Okay. So now that we have that, and we know it ranges from 0 to 1, okay, with 0 indicating that the model explained none of the variance, right? 1 indicates when we have 100%, it explains all the variance. So that's a good model, right? So again, R-squared just represent the goodness of fit of the regression model to the data. Okay. So again, from here, we can see that a random forest has a very high value. And this indicates that it's less than 50, but it's better than all the different R-squared represented here. So we can say this kind of indicates it fits the data well, meaning that there's a large proportion of the variance in the dependent variable quality that is explained by the independent variables in the model. Okay. Conversely, we can see that KNN here has a very poor R-squared. This is indicative that the model does not fit the data well. Okay, that just means the independent variables in the model do not explain much of any variance in the quality, variable, which is the independent variable, right? Okay. Similarly here, RMSE here, another commonly used evaluation metric. Okay, so we just take the root square, the square root of the average of the square differences between the predicted variables and the actual values. So a lower RMSE again here, let's see. So the higher here means just low, okay? But a lower RMSE here, in our case here, we have random forest, sort of gives us the lower RMSE, just indicates that the model's predictions are more accurate and closer to the actual value, even though they're not very, not very good, but we want to pick the lowest. Okay, so all in all, we can just say here, random forest is actually a good performer. So from our analysis, our conclusion is the strong performer. Okay, in all the many scenarios. What makes it a strong performer? This is actually an ensemble method, right? Which aggregates the results of many trees. We saw that we can specify we want to use 2,000 trees. Okay, and it's actually robust and it's not affected too much by overfitting. Unlike decision tree here, you can see clearly here, it's very prone to overfitting, right? And the good thing about random forest can handle both categorical and continuous variables, right? Next best here, we can see SVM also performs very well, okay? Means it can handle complex data with high dimensionality, right? And the good thing with SVM can also handle both linear and nonlinear relationship, okay? And then we can see KNN here, followed by, linear regression, or what we can say rigid regression here, didn't perform very well. But again, rigid regression here, it's worth noting that, if fine-tuned well using the regularization parameter, usually it handles multi-collinearity between variables, okay? And that can just helps it to mitigate the risk of overfitting. Okay, so that's just how to assess the model performance, and using this table, you can actually summarize and pick, the best algorithm. But remember, this doesn't stop here. You can continue with the feature engineering and fine-tuning to improve the performance. So this also depends on the type of data set, okay? And you can try different parameters, and compared with cross-validation, again, we can see here still random forest. So I already ran that with cross-validation, still performs much better. SVM, so in the event that you see that the cross-validation doesn't perform very well without, that means your model is actually overfitting. So you might want to change some parameters here. Okay. All right. And then lastly here, we can use the var import plot here. So essentially this plot is just, so I try to include this here and pass the RF model, okay? Just shows the importance of each predictor, the variable model, okay, as depicted here. So the plot here just shows the variables sorted in descending order of importance, okay? So with the bar here going from left to right, this just represents the magnitude of the importance. You can see alcohol here has a high magnitude of importance. So this plot is very important, especially when you want to select those features that have the most importance in your model. You can select it, it just allows you to visualize, and you can actually helps us to better interpret the model. Okay, so in summary, this just helps us to visualize the variable importance of a random forest. Okay, and this can be very powerful in understanding what the model is doing, and helps you to make data-driven decision. And that concludes this video on regression analysis.